my great pleasure to introduce our speaker, Dr. David McKee, who is CTO at Counterpoint Technologies and co-chair of the Digital Twin Consortium Capabilities and Technology Working Group. Thank you for joining us today, David.
Thank you, Meg, and it's a pleasure to be here. So let me just start with a quick overview of what we're going to cover in the next sort of 20 to 25 minutes or so, and outline really exploring what was published in that paper and dive into some of the details behind that. We're going to start by laying out the objectives, the thinking that went into defining this architectural framework, what we were trying to achieve, refresh our memories on some of the background, and then step through the key building blocks of that framework and the details you can find in the paper. We're then going to touch on some of the things at the end of the paper around digital twin systems maturity and some of the use cases, really hinting at the next steps and the future direction where we see digital twins moving, but also the adoption of digital twins. So first of all, let me lay out some objectives. The key objective with this framework, and also the paper, was to lay out something that is easy to consume and can be consumed by anyone in an organization, whether you are an engineer or whether you are leading that organization. And one of the key things we're trying to mitigate is providing a deeply complex, thousands of pages technical report that actually only your most experienced engineers can consume, but also not miss out on some of the important technical details. So this is the first piece of work in a long stream of work, and we'll talk a bit more, I'm sure, about some of those next steps in moving forward. So first then, let me start with some background. And the background to this really is a bit of a refresh as to what are the core elements of a digital twin. And here at the Digital Twin Consortium, we've spent a long time thinking about this, collaborating with a lot of our colleagues across numerous organizations around the globe. And the key elements that come out of the definition of a digital twin that we published a couple of years ago now are this concept of a virtual representation, the significance of the real world, and the importance of synchronization. And let me dive into that briefly in terms of the definition, because this is quite key in terms of what are the key building blocks that we then derive. This is the definition that I'm sure many of you are familiar with. A digital twin is a virtual representation of real-world entities and processes synchronized at a specified frequency and fidelity. You can already see there's those key elements that I pulled out on the previous slide in terms of the representation, the real-world entities and processes, and the synchronization. We can then step through and talk about the importance of impact, importance of application, and realizing that value by transforming businesses and effective action. And we'll see this through the use of applications and so forth in the framework. Then we build on that and say, hang on a minute, how can you have a digital twin without data? And we have real-time data, we also have historical data, and we pull those two separate pieces out into two separate elements within this framework. And that's going to be quite significant as it defines part of the right-hand side of the model. And then again, emphasizing the implementation, you can't have a digital twin without having somewhere to run it. I wouldn't be able to be here with you in this webinar without running on some IT system. And easy to forget, but an important part when we come to designing these architectures is the IT and the OT, the operational technology systems involved. So what we're gonna do is we're gonna pull each of these elements out and understand that the key constituent parts of this are that virtual representation, the need for synchronization, the importance of data, and the IT, and so forth. This leads us to a simplified framework that you can see in this funnel diagram here, where we have applications and services. We recognize the challenges and the importance of integration and interoperability, which also will include the elements of synchronization that we'll get to later through the service interface layer. And then at the heart or the core, depending how you want to define it, we have the virtual representation. And this all runs on IT, OT platforms. So hopefully you can see that this maps directly back to the definition. And this is all about ensuring consistency in language, consistency in the semantics as we're talking about these systems, so that when we're explaining what digital twin is, we can map that all the way through to the architecture, the implementation, the deployment, so that all stakeholders are consistently using the same language as we go through this. One of the separate activities that we've been doing at the Digital Twin Consortium, you can also find a glossary on our GitHub site, which goes through a lot of the terminologies and adds definitions to each of these. So do feel free to go and have a look at that as well. So let's expand on that funnel, that simple diagram with those 4 layers, where we have applications at the top, we have those service interfaces, then we have virtual representation. It runs on IT/OT platforms. We can expand this into these layers. So again, we have applications sitting at the top with integration service interfaces, with the virtual representation, IT/OT platform. We also introduce here 2 additional really important concepts. One being the real world. And if you remember back to the definition, a digital twin is a virtual representation of real world entities and processes. So if we don't account for the real world in this architectural framework, we're completely missing the point. And if we want to be able to rely on these systems, on the predictions, the forecasts that digital twins are used for, we have to be able to trust it. It has to be secure, it has to be governed, it has to be managed. And we have to take that into account as well. In the paper, we then expand on each of these sections. And what we don't do then is we don't go into the next level of detail yet, because we recognize that there are a myriad of different ways, different vendors you can use to build these systems. However, we do in the appendix talk through some of the most commonly adopted. We're not advocating any one particular solution, but we looked at the most commonly adopted platforms for building digital twins over the last 2 years, mostly been cloud-based platforms. And we show how those platforms relate to this framework. So particularly around the IT and OT platform piece. So looking at cloud infrastructure, looking for data storage, data lakes, networking, compute, and GPUs, that type of thing. So fundamentally, we have this IT/OT platform without which we cannot run digital twins. We have nothing. And we have to recognize that there is a really interesting piece here around the tooling stack and what software tools, depending on what you're running and what you're doing. If you're in the world of fluid dynamics, you will have quite a complex tooling systems there with CFDs. It could be FEA tools, you name it, probably then running on HPCs. And then there is an interesting gray scale that goes between this IT/OT platform and the software tooling into the virtual representation. And we'll touch on that in a moment. What is quite key is we reviewed this model and all the remaining pieces of this against all the different vendors that are members within the consortia, and to look for how this matches and marries up with their solutions. There are, of course, some variances, but for the most part, it fits quite well. Within the virtual representation, now remembering that the virtual representation sits at the core of the digital twin, it is really, this is where all the intelligence is happening. We have the concept of modeling languages, and that correlates directly with the tooling stack that one would be using. We then break out 2 different representation types. And this is quite important. We have the stored representations. These are your static models. And then you have your computational representation, where we're referring more to actually running the simulations, the actual simulations themselves. There's an understandable conflation of all of these 3 concepts, because depending on what software platform, software tooling you're using, you may find that all of these are wrapped in under one thing, and that the modeling language you use is also the representation for defining your model, and that is also how you run a simulation. So we understand these things may well come under one single unit if that is the implementation you're adopting. But more often than not, particularly when you get to complex systems, we can break these out, and it is a useful exercise to break these out and understand them. or separately. On top of that, we then have the synchronization mechanisms, because without these synchronization mechanisms, the digital twin is just a model. It's just a simulation. And we'll come later in this webinar to look at the maturity piece and understanding the role of data to define a digital twin and really elevate it above what could be fantastic models and simulations is critical. Within the synchronization mechanism, and this flows both directions, and it has to be a loop, is we identify that there is synchronization mechanisms with the real world. So this could be IoT systems, could be camera feeds, a whole range of different things there. But there's also a level of data interoperability. And the data interoperability will come in quite significantly when we think about other data sources that kind of, one would think they're not really part of the real world, but are they part of the digital twin system? They kind of sit in that gray space. And I'll talk about a couple examples of those in a second. Once we have these mechanisms for synchronization, we need these interfaces to allow this data to be integrated. We need these functions to do transformations on data and transform it into the appropriate different functions. And this becomes particularly prevalent when we look at systems of systems and look at federated digital twins, composable twins, and so forth. So we introduce a whole lot of different elements here where we look at integration functions and representations within this core representation piece, where how do we integrate these different models together and look at whether this could be understanding how time is represented in terms of time steps within different simulations, so you deal with consistencies, or it could be looking at the service interfaces between different tools, between these data feeds and these synchronization mechanisms. And then this will feed further up into the application layer in a second. I mentioned the role of external data sources and that data interoperability. And one of the key things we found, and this was a piece that we initially missed on our first pass of doing this framework, was that actually when you go to deploy any real digital twin system, you find that there's a whole load of business data or organizational, operational data that could be anything to do with personnel, stakeholders, users, and it could be systems information that isn't necessarily part of the digital twin itself, or at least not obviously, but is right on the edge. It could be defining metadata. It could be providing that additional context for what you're recording. So these are typically found in databases. This could be open data sources, or it could be within your organization that you need to connect to. More often than not, these would have to be synchronized at a different frequency, different fidelity. So one of the things that's worth mentioning in terms of synchronization here is that in the original definition, we talk about synchronization at a specified frequency and fidelity, and this comes down to the use case. So I previously supported a project in the UK where we're looking at planning for net zero interventions. The reality is, from a city's perspective, you could have live data streaming in about traffic volumes, but you can't go and install a new traffic light or solar panels or close a bridge instantly. You can only respond within a specified time period. So that defines the frequency and the fidelity with which you might respond. And that's one of the key things that's worth thinking about when we think about digital twins, is it doesn't always have to be real time in the way that many of us would think about it in terms of just being really fast. But I would define it as being real time in terms of it has to be fast enough to meet the deadlines such that actually the impact of the digital twin not responding back into the real world is not negative. It has to have that positive impact. And there's some great literature out there on terms of the impact of real-time systems and the formal definition of those, and applying those in those contexts will provide some additional context to how we apply synchronization, how we model synchronization, and what does or doesn't count as a digital twin. This is particularly important when we think about it in terms of different synchronization at different frequencies, depending on the different data sources. And then, kind of one of the final key pieces here is, in order to realize value, in order to realize impact, in order to have that synchronization back often, you need applications. You need a way to do something with it. Now, this could be dashboards. It could be ways to feed that back to a network operator, a power station operator on the ground, and it might be on their iPad that's just going to flash red, say you need to go and do something. That might be the response, or it might be an actuator through an OT system. But there has to be these application layer that realizes the value, that builds into those other organizational systems in order for this to be useful, to be applied. And this is where we start also moving up the technology readiness levels through digital twins to digital twin systems, and we'll talk about that in a moment as well. And one of the key kind of elements underpinning all of this are these concepts of security, trust, and governance. I'm not going to dive into these now. There's been previous webinars, there's previous papers published by the Digital Twin Consortium diving into these and really kind of pulling these out with respect to digital twins. So I would invite you to go and explore those in further detail. So I'm now going to kind of, that gives hopefully a flavor of the architectural framework. You could dive into detail in the paper. And I'm going to take a pause there and now dive into just thinking briefly about digital twin system maturity. And I alluded to this with my slight tangent around, is it the digital twin or is it just a really fancy model or simulation? And that is a hard question to answer, and can also be quite a weighted question, controversial question. But this is how we try to think about it in terms of, and this is very much open for discussion and something that we're continuing to research and explore, is looking at technology readiness levels as one potential framework for modeling this, and considering that modeling and simulation sits at the lower end of this, because models and simulations are likely to be part of digital twins almost always, and they will probably be built as one develops your digital twin system. So as you build your digital twin systems, you're going to be building models and simulations. But until you actually include data, until you start actually building off real world data, you're nowhere near a digital twin. It could be a fantastic model, but it isn't based off the real world. At some point, we go through and it becomes a digital twin. It's based off real world data. You can feed it, you can get information from it, you can get impact from it. But until it is then integrated with all those other systems in your organization, that it actually becomes operational, and you're not thinking about a digital twin system. And there's a lot of different ways we can think about that, but we don't start seeing value until we get to the top of the TRL levels, and actually seeing it in a proven operational environment and taking a systems level view. This table is in the paper, and this is a initial view at what that could look like, and always welcome feedback on this, as on any of the other content in the paper. So we look at how models and simulations and all these pieces correlate to the different core elements of the architectural framework. And we can see, we talk about models being within the virtual representation, simulations as well. We then pick some example applications here. We've just pulled our dashboards as a very common example. So, well, actually, this is the application layer. It correlates to the data, correlates to the synchronization, the systems integration piece. And then digital twins there have everything, except they're not necessarily fully integrated with systems. It's a bit of a grayscale, so take it with a slight pinch of salt in terms of this, because it does depend on your actual application. And then we get to full maturity of digital twin systems. So as we then think about digital twin systems, we come back to this diagram, and we can start to put a box around this and say, actually, when we're thinking about any individual system, we need to think about all of these elements. And that then allows us to modularize, compartmentalize, and take a systems of systems approach, so that we can think about, actually, as we build digital twins of cars, for example, we can think about digital twin of the engine. We think about a digital twin of the transmission unit. And then we could think about a digital twin of the powertrain, including both of those elements. And then we'd go up to vehicle dynamics, and then we'd go up to full vehicle. So we could have multiple layers within this, depending on the complexity and the fidelity required. Because actually, if we try and model some of these really fascinating systems that have massive impact, we shouldn't do it with just one system. The human mind doesn't really allow for that. So what I'm going to now just talk through is just going to fly over a couple use cases and then leave time for some questions. In the paper, we have 3 use cases, and I'm going to talk very, very briefly to these, the details in the paper, and we're always happy to point you to the members who are leading on these use cases as well. So we have a kind of a fascinating case here, which is looking at the manufacturing distribution around coffee. So this is a great example that takes a very traditional systematic systems approach to digital twins, and the detail in it here, and you'll have to be willing to spend quite a lot of time looking through this. So take a SysML approach to modeling all the constituent parts, putting that through. In the paper, we map each of these elements then across to the architectural framework, just to give an example of how you could map your own architecture, your own system, your own operation and business in the same way. And we do this across 3 examples. We do this looking at quality control and manufacturing lines. Again, another example here where we pull out the key elements, particularly looking at actually what are the processes for acquiring data, really, because that was one of the key challenges in this example, that orchestration, and mapping that through here. So we can see this particular challenge here in this example was the data piece, and then the orchestration of all those systems. And then the final example we have in the paper is talking about emergency services and looking at how that relates to from a trust perspective, which is again a really important of actually, if we're going to use these in real world scenarios, we have to be able to trust them and pull them out from there.
Thank you so much, David. Thank you for your time. If you are interested in membership and the benefits of joining the Digital Twin Consortium, you can learn more at our website, digitaltwinconsortium.org.